that you should have graphed on your paper. So if you haven't graphed them, graph them. If you did, check with neighbors, and then we'll make sure that all of our graphs match. I have to draw lots of points because I can't draw straight lines. So. All right, so your graph should look something like this. Again, if you are struggling a little bit, some patterns that you should be able to see. So first of all, with absolute value, just knowing where the vertex is and what the slope is, you could graph it very quickly. So -1, -2 is our vertex. The sides have a slope of 2, and it's positive, so it faces upward, so up 2 over 1. With our parabola, the vertex is at +2, +3. I knew that. And the only other transformation was that it would go downward, but it didn't change like any of the distances of the points of the parent function because there was no stretching or compressing. So I felt like I could do that in one step if I just plotted the vertex in one point. And then I knew 1 over was 1 away and 2 over was 4 away, because that's exactly how it is on the parent function, like that you guys just graphed. I just drew it downward instead of upward because of the reflection. And then for the square root function, this had no transformations except for the shifts. So basically, if I could get the vertex in the right place and just draw the function how it normally is, I have it done. So 3, -2 is where the vertex is. The next point's 1 away and 1 above. The next point would be 4 away and then 2 above. Okay? So is everybody okay with how we got these? And how once you become more familiar with them, you could do more things in one step. But don't try to do it if you're not familiar, then you can still graph each one step by step. Okay? The point in doing these 3 separate graphs is today we're going to do piecewise functions. So I'm going to skip ahead for a minute to show you what we're actually graphing. So we're actually going to try and graph a function that looks like this, which is crazy, right? It doesn't even look like a single function. It actually looks like 3 different functions, right? What it is graphs in real life don't always follow a perfect pattern. Maybe part of your graph looks like this, but then all of a sudden it goes like this. Okay, maybe it comes back down, and then maybe it goes like this or something. Maybe there's different situations that are occurring that are causing different types of movement or for it to follow a different pattern. So when we want that to happen in math, we basically say, like, hey, the first piece looks like one of these, but it only happens in this part of the graph. Then the next piece looks like this, and it only happens in this section of the graph. And the next piece looks like this, and it only happens in this section of the graph. Okay? So to build a better understanding of that, notice that we're trying to graph one function that has 3 pieces. Okay? These 3 pieces are the same as the 3 graphs we just graphed across the top of our paper, because I want you guys to understand how we're deciding what to graph where. Okay? So now I want you guys to take a highlighter or some different color or something that will stand out. And we're going to highlight each function, but only over a certain domain. Okay? So that's good. Okay, so this is the entire absolute value function. Okay, what is the domain of this function normally when we just graph it by itself? All real numbers. Okay, but then I gave some instructions on your handout. Okay, I said to graph number 1, I want you to highlight the portion of the graph that's in the domain x is less than 1. Okay, So think about where x is less than 1. That means look on the x-axis, okay? Here's 1. Sorry, I have my highlighter on, okay? So here's where x is equal to 1. So if I only want to highlight the part of the graph where x is less than 1, I basically want to highlight this portion of the graph. And this part can go forever, because is x still less than 1 for all these points? Yeah, because it's moving in this direction. But do I want to go past this point right here? No, because x would be more than 1. And actually, at that specific endpoint, somewhat important, this endpoint right here, should we make that point the last point on our graph or not? So it is lined up with x is 1. So it is where we want to end. The question is, do we want to fill it in or keep it open? Like, are we including this point or not? No, because I said where x is less than 1. So that means all the way up to where x is 1, but don't include the point that actually has an x value of 1. So on our graph, that's going to end right here, and we would make that like an open point. Okay? So basically, we're taking the graph we already knew how to build, but we're like cutting a piece of it off, like saying we don't care about any of the graph over here that we haven't highlighted. That part is no longer going to exist if we restrict the domain and say we only want the part that's where x is less than 1. Okay? All right, so on the next graph, I asked you guys to highlight the part where 1 is less than or equal to x is less than 4. So basically, the part of the graph that lies between where x is 1 and x is 4. Okay? So I'm going to go ahead and do that up here. So here is where x is 1. Start that there. And I'm going to go until x is 4. 2, 3, 4. So like that's where that point is on that graph. Like that. Okay? That's the part of that graph that falls between where x is 1 and x is 4. If you drew those two lines where x equals 1 and x equals 4, that's the part that I have highlighted along the graph. Okay? And then again, we have to have that discussion about endpoints again. So the first endpoint at 1, when you look at the way I wrote where I wanted you to highlight, the 1 is less than or equal to x is less than 4, is 1 going to be an open or a closed circle for this graph, the way that we've written the inequality? Closed, because it does say x could equal 1, right? It says 1 is less than or equal to x. So this point is actually going to be included in our graph. Okay, so I do want to include that point. And then we know we were stopping at 4. Are we including 4, or is it an open point at that end point? So if you look at the inequality, it says x is less than 4, no equal sign on that part of the inequality. So that means this is an open point. Okay. All right, and then for the last graph, I wanted you to highlight the portion of the graph in the domain where x is greater than or equal to 4. Okay? So there's no second boundary in this one, just where x is greater than or equal to 4. So 1, 2, 3, 4. From 4 over forever, okay, that's the part of the graph I want you to highlight. So from 4 over forever. So it's going to go forever along that line. Sorry, highlighter's a little bit too thick. Okay, and then again, endpoint. Did it say x was greater than or equal to 4, or did it just say greater than 4? Greater or equal to. So I actually am going to include this endpoint where I started, where x was equal to 4. Okay. So on the next slide, and for you guys right below where you graphed it, you see one problem that basically encompasses everything we just did. So mathematicians are too lazy. You've seen the way that they write everything in math, right? Everything is shortened, abbreviated, okay? Everything has something short for it. There's no way that when they want you to graph those 3 separate things on the graph that they're going to do what we just did. They're not going to say, graph this whole one and just look at this part of it. Then graph this whole one and just look at this part of it. Way too much work spread out all over the place. They want it condensed into one thing to look at together. So that's why they write this notation. This is technically one function, okay? But again, this function has 3 pieces to it, okay? So what we're going to do is we're going to graph each of these pieces on the same graph, okay? So we're going to go back you guys have already highlighted everything, because notice the 3 graphs I had you graph are what's right here. I want the first graph, but I only want it when x is less than 1. That's the part that you highlighted, right? Then when x equals 1, I don't want that graph anymore. I want to switch to this graph. And I want to keep this graph going from 1 until I get to 4. That's the part you highlighted on that graph. But when I get to 4, I don't want to graph this one anymore. I want to graph this new one from 4 on. Does that make sense? So basically, we want to take everything you guys highlighted, and we want to put it together on one graph. And this is how a mathematician would write what they wanted you to do, instead of writing out instructions like I had you do. So this is their set of instructions to do everything that we just did. Okay, so I wrote it out like that so you could understand a little better what it was actually asking you to do. But now we're going to build it right here the way they would want us to build it. So you're going to go ahead and transfer all the information that you have from each of those graphs that you did right here, because you already did all the work. So do you see in graph number 1 that you already graphed this shape? Yes. Okay. And the part that you highlighted is this shape, but only for this domain. We only want to put it on the graph when x is less than or equal to 1. So basically, when I reach 1, when x is equal to 1, sorry, that's negative 1. When x is equal to 1, the graph should no longer go any further to the right of that point. Okay? So go ahead and copy the part that you highlighted from the first graph onto this graph. Okay? So the first piece of this piecewise graph, so I'm using the vocabulary you're now going to hear them use. This is called a piecewise function because it's one function broken into pieces. The first piece would only exist in this part of the graph. It's the normal graph we're used to, but only highlighted up to this domain area. Okay? The second piece was this graph, but we only want it between these sections. Again, you already highlighted that in your first graph, so copy your second section of graph onto here. Now, one thing I want to point out when you go to do that, notice that you stopped at the point 1, 2 on this graph and you made it an open circle, right? This second piece happens to start at the same point, 1, 2, and it's a closed circle. So when you put them together, one was open and one was closed. Is that point going to be filled in on the final graph or no? Yes. So it didn't exist in this piece, but it does exist in this piece. So once you put them together and put them on top of each other, you're going to see that point filled in. Okay? So go ahead and copy that second highlighted portion. So I filled the parabola in, but only between 1 and 4. Then I stopped the graph because at 4 I would start this new graph. Okay? So again, this is the last equation we looked at, and we specifically already highlighted it for the area where x is greater than or equal to 4. So, basically, we now want to come and we want to start here and put this here. Now again, this graph ended at the point 4, negative 1, and it was open. This graph starts at the point 4, negative 1, and it's closed. When you put that closed point on top of an open point, it's going to appear that that point is filled in on your final graph. Okay? So we're going to go ahead and do that. So at this point, we would fill it in. The next one would be like over there somewhere. So that is the graph of this function. Okay, Stephen? Mm-hmm. Good question. Okay, so this one I very carefully chose the numbers in the equation so that they connected. Sometimes the problems are like that, and sometimes they don't. Sometimes this graph will end, and this one might start somewhere way up here or way down there, and that's why it's important to know whether the endpoint was open or closed. In our mattering because they always overlapped, but they won't always overlap. And that's okay if they don't connect. Okay? Yeah, so like if these didn't connect, we would have this part and it would end right here, right? And then this other part might start here and go like this and end right here. Oops, this was open, okay? And then maybe the square root like started down here and went like this or something. That could still be a graph. It would just maybe affect your domain or range, okay? All right, so does everybody understand what this means, this notation, okay? So it's a little hard to understand, but I think I came up with a better way this year when we like graphed them each separate and highlighted it. I think it's a little more clear what they're trying to tell you when they tell you all this stuff right here. Okay, so you have a couple of options when you want to do this depending on how good you are at graphing. You could literally do all of these problems like we just did. You could think of each piece, each graph in its entirety, and then just kind of erase or cut off or highlight the parts that you want or cut off the parts you don't want of the graph. Or if you get really good at it, you can read and put them all on here at the same time. Obviously, that's how I do it, but I do math every single day of my life and have since I like began school in kindergarten. So probably not fair for me to judge how I do it with how you want to do it, right? So choose what's going to work with you. What we did is probably the most basic understanding of it, and you could do that for every problem. You could use a highlighter on your test if that's helpful to you, and you could just go through that process, okay? All right, we're going to write the domain and the range for this function, because these ones can get a little bit tricky because, like Steven said, there could be gaps in our graphs, which could make it a little bit difficult to kind of get the domain and the range. So first, domain. Remember, that means from left to right, okay? So is there anything we skip, or is there any point where our graph completely stops and does not go beyond from the left to the right? So we're looking from left to right. So like this continues forever in this direction. This continues forever in this direction. So we're good as far as we keep going. And was there any x value that was like skipped? Like for that x, there's no points on the graph. Nothing. Okay, then our domain is going to be all real numbers. Okay. Now the domain for each part is right here. Okay? So if somebody asked me, like, what do you get when you plug in 0? I don't plug 0 into all of these. Which of these could I actually plug 0 into? Only the first one. Why only the first one am I allowed to plug in 0? Because this one is for x values that are less than 1. This one's for x values between 1 and 4. Is 0 between 1 and 4? No. This graph is for x values bigger than 4. Is 0 bigger than 4? No. So an x value of 0 only belongs with this graph. And we'll get more into that later, but so that you can understand. Like each piece has their own domain, but the domain of the whole graph you're going to see after you draw it all out. Okay. All right, and then what about the range, going up or down? So is there any limit going upward? Is there any maximum value that you hit and do not go past? No, because this is going to climb forever, right? It'll take a really long time, but that piece will climb. And this piece is climbing really fast, right? So we'll definitely go up forever. Is there any minimum point that you hit? Yeah, so this is the lowest point that we reach. Definitely -2. Is there anything that is skipped between -2 and then going upward forever? Is there any place where there's like a big gap and we don't hit any of those numbers? No, there's a way to hit everything. So our range is from this point and above, we will hit every point. So basically, all the y values are greater than or equal to -2. Okay. All right. Questions about the process? No? Okay. Then to address what we addressed before, or what I just talked about here, how each function has its own domain, I'm going to go back to what would have been a math moment, but you don't have to write it down as a math moment. You can add it like on the side of this sheet somewhere, or you can write it on a separate sheet. You're not getting new homework tonight, but you'll get new homework tomorrow night. And it asks you some questions like this, so I just want to make sure that we can do this. So now that we understand what that means, so if I would have just put this up here, you would have looked at it and been like, what the heck is that? It looks like a function, but it has all these pieces. Now we know this is a function that's made of how many pieces? 3, okay? The function itself might have some crazy domain or range, but each piece has a specific domain. So the first piece can only be used for x's that are less than 0. The second piece can only be used for x values between 0 and 4. And the third piece can only be used when x is bigger than or equal to 4. So we're not graphing this one. I'm just asking you to do some calculations, but this is going to help me make sure that you actually understand how to read it now that we talked a little bit about what each piece means. So when it says find f of negative 3, this means I'm plugging negative 3 into the f function. But the f function consists of 3 pieces. Okay? Which piece am I actually allowed to plug negative 3 into? The first, the second, or the third piece? The first piece, because the first piece only works for x's that are less than 0. And this x value is less than 0. Do you guys understand that? So you're not plugging the number into all the pieces. You're only plugging it into the piece where you're allowed to plug in this x, the one that matches with it. So finding f of negative 3 here really means only plugging into the piece that looks like this. Okay? So all we're doing is taking negative 3 and squaring it. Negative 3 times negative 3 is positive 9. All right, what about finding f of 5? Which piece am I going to plug into? Right. The third piece, okay? Because the third piece allows all x values that are greater than or equal to 4. So basically, you're looking at this number right here, and you're trying to decide. You're not even looking at the first part yet, but the little second parts where the inequalities are with x, where does it fit? So 5 is a number bigger than or equal to 4, so in the third piece is where it would fit. So I'm not calculating them all with 5. I'm only using the third piece, and in that piece, I'm plugging in 5. So 10 minus 3, which would give me 7. And then these would all be points on my graph. My graph should have the point negative 3, 9. It should have the point 5, 7. Okay. Might be some weird stuff going on in between the points, as we saw before, but it'll have it. All right, what about 2? Where does 2 get plugged in? First, starting from the top, first, second, or third piece of the equation? Second, because as I look, is 2 greater than or equal to 4? No, then I can't plug it in the third piece. Is 2 less than 0? No, then I can't plug it in the first piece. But is 2 between 0 and 4? Yes, so I would plug it in the second piece. So again, I am not plugging it in everywhere. I'm only plugging it into the function that looks like this. So I would just get square root of 2. All right, so just kind of a thinking question here. What if I wanted to calculate f of 0? Do I plug into the first piece, the second piece, or the third piece? Eliminate one. Which one are you not going to plug 0 into for sure? The bottom one, right? It has to be numbers bigger than or equal to 4. That doesn't even kind of like go with 0. Okay? But then does 0 belong with the first or the second? Which one actually says x can equal 0 in that function? The second one. So that's where I would plug it in. Okay? So this would be this, which would be 0. Okay? What about if I wanted to plug in 4? Okay, so it's between the second and the third. Which one actually says you can equal 4? The third piece. So I'm plugging 4 into this. Is that okay with everybody? So are we okay with the notation? We understand now that functions don't just have to come as one thing. They can actually come with this whole list of bunches of different pieces, anywhere from 2 pieces to like as many pieces as someone wanted to include. Okay? But when you include multiple pieces, you must include a domain that goes with them. Like where do these pieces operate on the graph? Okay? All right, so let's try one more graphing example today, and then we'll finish tomorrow. All right, so how many pieces does this graph have? 2 pieces. I got to graph 2 things. First piece is shaped like a what? 3x plus 1. mx plus b line. Okay? Yeah, okay. So first piece is a line. Second piece, x squared minus 2 parabola. Okay? So here's another option of doing these if you just want something kind of temporary to put on here and you don't want to draw out all the graphs and highlight it. What is kind of the pivotal point where you stop graphing one of these and you start the next piece? 0, right? So I'm going to go ahead for myself, and what I'm going to do is put something on my graph that totally does not belong on my graph, but is just for me to kind of mark that I'm going to switch and start graphing something else at 0. Is this yellow dashed line in any way part of my graph? No. This is totally Miss Dahl's thinking process, how I'm going to get through this, if I'm not going to do what we already did. Option 1, graph them all separately, highlight the parts with the domain, put them together on one graph, right? Option 2, for those of you that don't like that, think about your graph in different sections, and then go graph each piece in each section. So on this side, where x is less than 0, I will be graphing 3x plus 1. Is that okay with everybody? Then on the other side, when x is bigger than 0, I will be graphing x squared minus 2. Sometimes how you know how to graph it puts things in the area that you don't necessarily want. But you could do it as long as you erase pieces at the end. So like when I graph a line, I graph the y-intercept, right? 1, okay? So 1 would be like here. And then it has a slope of 3, up 3 over 1. Oops. Do I want to point over here, though, for that graph? No. So I'm going to make sure I continue it so that it's going in this other direction. Again, I can't draw straight lines, so I need to make lots of points, so I'm sorry. 1, 2, 3. Okay, till I get a good enough idea of what's going on. So there's the line. Notice I didn't connect it to this other point over here because I don't want it to cross this boundary. I also need to think about this end point right here. Should it have been closed? I just drew it because I was drawing it. But should it be closed or open? So for the 3x plus 1, is it equal to 0 in that domain or no? Can x equal 0 next to the 3x plus 1? Yes. So at 0, I want. If you have to, you can say like it equals on this side, so you should have to close it. Okay? Or you could say like this one's a closed and this one's an open. Okay. All right. X squared minus 2 is a parabola. Where's the vertex of that parabola? Negative 2 is the x-coordinate or the y-coordinate of it? The y-coordinate. It doesn't have an x, any shifting left or right? So the vertex is just at 0, negative 2. And I'm going to make that point open. I know this because it's on the boundary, and this one doesn't include 0. So again, you can note like this. You can look back at the function. Okay. Now, this is the vertex of the parabola. Normal parabola goes up on the left side and up on the right. Am I going to draw the part on the left side? No, because this graph only exists on this side for my piecewise function. So then I'm just going to use the pattern of the parent function. I know that 1 away from the vertex, there's a point 1 above, and that 2 away from the vertex, there should be a point 4 above. I know that because I have memorized the parents that you guys just graphed on the quiz. Right? And then I would draw my parabola for that part. Okay? We're going to finish the notes tomorrow. There's 3 more examples. We'll work on this before we get assigned homework on piecewise functions. Okay? Make sure you guys finish your homework number